Hi everyone, welcome to this session. Okay, then once we have found the principal component, right, then we can multiply our data to project on that particular axis. Okay, so let's say we found the principal component. This is the new dimension. We take the existing data, do the dot product with it, and we get the new set of features. So what we are doing is we are taking the existing data and saying that pick this, saying that project this data across this axis. Okay, pick this data, take this data and project it across this axis. We do that for all of the axes. Okay, so original training data set X can be projected onto the first D components, WD, right? This is composed of first D columns of the transpose V obtained in SVD. So the new ones, right here we are basically multiplying. This is collection of all the columns that you want to keep. So it's same thing like either you take this column and multiply with each of them separately and then put them in a matrix, or you just create this full matrix and then multiply with the data, right? So here WD is equals to, WD here is equals to the first D columns of the transpose. Yes, W1 is C1, correct. Okay, so instead of picking all the columns, we'll just ignore the last ones and we just keep the first few ones. And that's a choice that we need to make, that how much variance is what we are ready to drop. So PCA involves two steps. One is SVD. All right, that's correct. So we, first column, yes, W1 and V, yes, that's correct. Thank you, Deepak. Thank you for sharing that part. Yes, so PCA essentially involves two steps, SVD and projecting of the training data set onto the orthogonal components. So here we find that direction and then here we click the photo. Okay, here we find the camera position and here we click the photo. Those are the two steps. So, and of course, we get up and go to the center of the crowd, right, in the front, and then we basically figure out which one is giving good covering everybody, and then we click the photo, right? So that's PCA. And so PCA also provides you the, either you could do it by yourself, like first do the SVD, do the projection, or you can do combined PCA in a single shot. Okay, so this and this are both equal. In the first one here, we had to first center it, then do SVD. SVD is basically a linear algebra algorithm, and then here we are picking those number of components, like first two components, and then we are centering it. We are doing the dot product, so this is our outcome. Okay, and in case of scikit-learn, the same thing is done using inside the PCA. PCA is basically taking whatever data you are giving it here. It is first performing this the mean and taking the data to the center, and then it's basically calling the SVD inside, and then whatever components you have defined, those many columns it's picking, and then doing the dot product and giving you the results. Okay, let's take a look. All right, so let's take a look at our notebook. It should be inside ML, inside machine learning, and there you will see the dimensionality reduction. Like here, this is what we are doing. So we can say run all above. Okay, so this is a simple way of doing it. And now after this, you can basically take this data set and present it. Okay. So take this data set and then you can start the training here. This is the transform data set, and that we can do with almost everything. Okay. So what you can do is you can do it on MNIST. Have we done it MNIST? You can try on MNIST. We did load, right? MNIST is it? Okay. You could give it a try on MNIST in your you know, time. What you can do is you can say as a good step. So what you do is you in case of MNIST, okay. Now when we were using MNIST on XGBoost, it was taking too much time, right? With XGBoost, it was taking too much time, right? So what you can do is choose only the accesses which have significant variance, okay, and then run the XGBoost again, okay, with 60,000 records and so on, and with maybe say 150 trees, and observe the quality of results. Okay, so you can consider this as a little assignment, though we would be doing the what do you say, doing one of the MNIST things towards the end. Okay, try doing this. So observe that the after we basically reduce the number of columns, the XGBoost will also perform better. Okay, and here basically you will also notice that the overall quality of results has improved. Okay. Question from Deepak is that after projection we'll get new data set with lesser features and then use the new data set with lesser features on XGBoost. That's right. That's exactly what yes, you got it right. So all you need to do is define your principal components and first try SVD and see you know, what are the various how many features, what kind of variance are you getting. Let me just go back up. I've done SVD here, right? So here once we run SVD here, you will notice the number of columns. I'll just show you that will happen. Okay. So here it generally shows you this, and yeah. So at every point of time, you can find out the variance ratio. Okay. It shows you that the first component in our case had this much variance, while the second one had this much. So it's safer to just drop the second one because second one is really low, right? So this is a ratio in the sense that it is out of 1. So all of these values, these variance, the total, it's not real variance, it's basically kind of normalized. It's basically a ratio in the sense that the one that is out of the max, what is the total? Okay, so it's that ratio in the sense that total individual value divided by total variance. Now using this ratio, you can easily figure out that the moment you can easily say that with the moment it goes below say 0.1 or let's say below 0.05, meaning 5% variance, then don't pick those excesses. Okay, Okay, one thing that you'll see that we will see these methods like sum. Okay, the cumulative sum is for what? Cumulative sum is for summation. Okay, so you can see that the cumulative sum is 1, then 1 plus 2, then 1 plus 2 plus 3, and so on, right? So 1, here you can see, right? And then plus 4 plus 5, correct? So this is called cumulative sum. Cumulative sum we did not discuss during NP, but you can take a look at the NumPy library. You will see that sum is a very common function. Then we have the argmax. What argmax does is tries to find out the place where okay. So okay, let me again break it to two parts. CS greater than 5, right? Okay, let me just show you this part. Okay. So yeah, so what we are saying here is that what is the location where the value of this is max, right? From here we kept on going, and this is the point at which we reached where this particular value is greater than 5. Okay, what is the max of these values? Okay, what is the max of these values? And yeah. Okay, so this way, that's what we are doing here. Okay, so here what we're doing is we are initializing the PCA, we are fitting our data, then we are taking a look at the variance ratio, then we are doing the cumulative sum, and then we are finding the position at which the cumulative sum is greater than or equal to 0.95, right? And that is the position that we are going till. Okay, so the position of such is that the moment we hit the let's say first one itself till here, okay, is going to be bigger than 0.95, and therefore it will stop at 0, and we print it on. Okay, now so it's a nice way of saying that keep going. This is nice way of saying that keep going until we reach a point where we have covered 95% of the variance. Okay. Question from Deepak is, after projection, we'll get a new data set. That's right, with less number of features. That's right. And then use this data set with less number of features on XGBoost. Yes. At the end of SVD projection, are we getting the final data set? No, we don't. Good point. After SVD, we don't get the final data set. Instead, we get only these new axes on which we can project. And if we do the dot product between the vectors between the principal components and our data set, we will get the new data. All right. So this is what we are trying to do here. Question from Robert is, what would happen if you did some processing on data set first and then run PCA? Would that be faster or have any benefits? All right. So of course we'll have to do the processing, basic processing, like converting data to like categorical variables to numeric ones that you need to do. And we can right, good question. And what about standard scaler? That should help. That should definitely help. Okay. Help PCA. It could be a little faster, but I'm not sure. I'm not sure. All I know is that SVD it'll be helpful for SVD because PCA is anyway trying to center the data internally. Okay. Great question. So here in this example, when we are looking at it, so there are 95.3% of the data that covers the variance. The first vector is covering the 93% of variance, and second one is covering only 4.6%. Therefore, we can drop the second column, second feature, and we don't need the second feature. Okay. So a common question is that how do I select the number of principal component? The principal component should generally explain 95% of the variance, right? So we keep on going from left to right till the point we get our 95% of variance, and that should be good enough for us. Okay. So a question from Deepak is, all right, Robert, was you able to explain answer your question related to the standard scalar? Okay, a question from Deepak is, but this is automatically dropped when we do dot product of projection and old data set. Okay, so your question is when we are using SVD, right? The singular value decomposition by ourselves, right? In that case, those who are getting confused between SVD and PCA, PCA is basically doing SVD inside it. It just also, it is all, SVD only gives you the vectors having the maximum variance, but you need to project your data, you need to translate your data onto those axes which are given by the SVD. And that's where the projection comes into play. So PCA does both, finding those axes and doing the projection, while SVD only finds the axes. Okay. So we need to drop these columns by ourselves. Okay. When we are using PCA, we can say that how many components do we want to use, then we can just use those many components. Let's just take a look at the PCA. Okay. PCA gives you to choose the ability to choose the number of components. Okay. But it doesn't give us the ability to. Okay. So in case you don't choose the number of components, it basically selects all the components. Okay. All right. And so you can specify number of components, integer, floats, or string. If you don't specify this variable, then basically all the components are kept. Okay, looks like this variable acts like the variance also. I see. Looks like it does that job for both. All right. So so though PCA doesn't give you that, you can actually skip specifying if you are not upfront clear about how many components to keep. You could do that. Let me just give one shot to this. So we could say number of components equals 0.95, right? And we are saying fit and so on. Okay, I'll just remove this part. So you can see that it has done this job automatically for us. Okay, if you want, say 96%, in that case it'll pick both. Otherwise, it'll pick the first one. Good. So this is a good discovery. Okay. So here, if you, all right, let me explain. So, all right. So so PCA gives you both functionality. The PCA algorithm from scikit-learn, it gives you both functionality. Either you could specify how many components you want to keep. Okay. Or you could specify nothing, right? Or you could specify it as decimal number, right? So if you do not specify anything, it will compute, it will basically keep all the columns, okay? It will keep all the columns and give you the variance ratio, right? It's not doing the projection to you. It did the fit, it did not do the fit transform. There are two parts to it. One is fit. Fit is learning about data, and transform is transforming the data, right? Now, there is second method whereby we can specify this. It does exactly what we are trying to do here. First of all, finding the cumulative sum from left to right, right? We are finding the cumulative sum, and then we are finding the point at which we have met this particular condition, as in where the value of this is maximum. Okay, so those are the number of dimensions that we want to keep, and afterwards what we'll do is out of these the variance ratio, now we know that after this, that how many components do we want to keep? One, and then we'll have to run PCA again. So in case we want to, in case we don't know how many columns you want to keep, in that case you'll have to go through this whole process. Or if you're very sure that we want to keep 95% of the variance, then you can just say that. So in your safest bet on MNIST dataset, what you have to do is just find this. Okay, just find this. Okay, just okay. Did we find MNIST anywhere? Oh, here it is. No? So there is here. All right. So let me repeat the Deepak's question. So I mean, to understand the whole process, if there are 1 million features, then right, if we have to manually drop say 1,000 features after PCA, then it'll be tedious. That's right. That's why you can use the variance ratio simply, and any function to give us the final matrix with lesser number of features. Okay, and yes. So this technique can be used in a single shot. You could simply say fit transform, and you will get, let's say here, right, x1. Okay, I'm just showing you this part. So we could say fit transform, and you will get the new data set here. So both the things will go together. All right, we'll do this quickly on MNIST, and you'll get the idea. All right, now let's go back to here. Okay, now, so calculating the principal components directly by specifying the variance explain. Oh, we have already had this in the slides. So we can specify the 0.95 as number of components, and we will get the results. Okay, another option is to plot the explained variance, okay, as number of dimensions. So if you are given the dimensions, we know that, okay, for till these many dimensions, we are covering this. So we do the cumulative sum and plot the cumulative sum as a plot, right? So this will come out to be like this. So there will be a point where as you are increasing the number of dimensions, the variance ratio will continue to increase. And when you have almost like 100% features, meaning all dimensions, then the variance ratio, total variance ratio, will go to 1, right? That's the total. So the explained variance ratio basically kind of becomes flat after a point of time. So let's take a look at this one. So after this point, it will become almost like flat. It's not going up. So that's around 95%. So we generally pick those many dimensions. Okay. So that's one way to look at it. And all right. For the above 2D data sets, we shall demonstrate calculating the estimated variance ratio, and this we have already covered now. Now, Another very important part of PCA is compression of data sets. Okay, not only compression, but not only compression of data set, but also it is used as one of the compression techniques, right? So it's a lossy compression in the sense that we lose some amount of data. Just like MP3 was one of the compressions which lost some lost some amount of information from actual music file, but but that was insignificant, right? So those kind of compressions are possible using using PCA too. Although there are many other ways. So there are many other ways to do the compression, but the PCA can also be used for compressing music, compressing images, and so on, right? The same strategy that we discussed can be used here. All right. So let me try to show you here. Okay, here we are trying to do the compression, and can I also show you here somewhere that let's say we have okay. So let's say we have to compress this and this data set. So all you need to do is do the standard train split. You got X train, X test, Y test. And after that, we could say number of components equals 0.95. And we say fit transform. This is our new data set. Okay. Will it take a long time? Okay, so this is our new data set. Okay, and let's just take a look at the shape of the new data set. So you can see that out of there are only 154 columns left, right? There are only 154 columns left. And on this, you can try XGBoost on this new data set. Okay. So is there plt.imshow? All right. How to we can use an np.shape, right? This is my first, right? And what we could do is we could say np.reshape and say 28. How many columns were there? I mean, we can't really show it. You know why? Because it has different set of columns, and those set of columns are not really, you know, do not have really anything to do with visualization. Okay, so try to visualize this image in some way, right? So it has 154. All right. So what is the square root of 154? Okay. So around 12. So can we reshape it? No. What if we reshape it? Reshape this particular image into, okay, np.reshape If we say 12, okay, we can't really visualize it, honestly. It's not, even if we try to portray it like image, then also it will not work, right? Okay, so why, I just want to, we have used reshape multiple times, right? So np.reshape. Cannot reshape array of size 154 into this. Why? Oh, probably it's not divisible. What are the 77? All right, let's just see if we can convert it into this. All right, why can't we reshape this into this size? Anyone? Yeah, we can use the same one. Okay, all right, let me try this. Okay, I was hoping that it will figure out by itself. Why do I need to worry about? Okay, so it doesn't make any sense. All right. So, but if you take a look at the first record on the actual data, it is this. Okay, X-ray new, and we are reshaping it 20 and 28. Right? This was the original, and after we have projected onto new axis, new set of dimensions, this is how it looks like. Right? This doesn't make any sense if you look at it from the other perspective. Right? Okay. So even then, you will be amazed to know that the algorithms will be able to make sense out of it. All right. Sounds crazy that we converted this image into this image. They all represent the same thing. Okay. What if we had 22 and 7? It doesn't still make sense. All right. So yeah. So the point is that when we are trying to translate the image into another dimensions, we can't really see it, right? We can't really figure out what happened. All right, specifically because what's happening here is each pixel we thought that we will convert it into all kinds of directions. Okay, all kinds of, each pixel was one dimension, And then we drop the dimensions. Now we have got this picture in 154 dimensions. And when we are trying to recreate or convert those 154 dimensions into a 2D, it's not feasible to display it in any way. All right. So that's the important part. And now I'm getting back to the compression. So similar thing, we could, now this data that you see here, we can run it through the XGBoost. You should give it a try and try to see if we can improve the accuracy, improve the performance on the MNIST dataset. Let's see if we can bring up the performance from 91 to something else. Okay. And also notice here that even when the number of components are, really this ratio that we are looking for is really high, right? Here, let's say even 98, right? Let's take a look at the kind of data set, the kind of components are needed. Okay, so here, even when we need 90% of the data or 90% of the variance, even then, there are only 260 columns required, right? And in case of 99, so in case of 99, you can see that the number of columns, even when we want 99% data, even then, only 50% of the columns are needed. 50% of the data is actually redundant. Okay, so try starting maybe 0.99, then 0.95, and try to do that trade-off. That if we drop these many columns, right? See, if you see that we have suddenly dropped 50% of the data, right? So the computation, since it's non-linear, right, will drop drastically, and therefore basically the XGBoost will become significantly faster while working on these half columns, while we are having almost same amount of data. We have almost same amount of data. Okay, so try this out. I'm just commenting this part in my code. So experiment on this part, and you will get, when you do a little bit of comparison between the performance of XGBoost on this kind of data and another, then you will get to realize that when the computation is heavy, it's better to drop the dimensions. Okay. So compare the performance, and you will also get to know that the outcome of MNIST should be better. It should be more stable. Okay, so take a look at that. All right, a question from Deepak is, dimension reduction will only increase the speed of computation, not the accuracy of the same algorithm. It should improve the accuracy also, right? Because when you have number of dimensions to be very high, the data is very sparse. And when the data is very sparse, what happens is that it ends up overfitting the data, and therefore it might give great results on training data, but not on the test data. So make sure to compare the performance of both with and without the dimensionality reduction. Okay. So I'm hoping that the accuracy will also improve along with performance. All right. Now, PCA can be used for the compression, so you can run it and you can see the compression here. Okay, so here we go. So here what's happening is we are importing the URL lib, then importing the fetch ML data, and then we are saying import the training split, we split it, and afterwards we initialize PCA, did the fit. Fit means just the training, not the prediction. and then we computed the CumSum, and we got the number of dimensions. So to cover 95% of the variance in case of MNIST, we only require 154 columns instead of 784, right? We can drop maximum number of columns. Okay, and right. Okay. So after translating the data, that data is actually compressed. Okay, when we are translating when we are translating the data is basically compressed, and right, because we have kind of half the data. All right, so only 154 features are required. Right, the compressed data set can be decompressed to the original size. Now, the point I was trying to make earlier is that when we try to plot the compressed data, it doesn't make sense to us. But when we want to really present it back, we can do the inverse. We can do the inverse transformation of this particular data set. We can do inverse, and then we can project it. Okay, so we can use PCA.inverse transform to do the inverse, and that way we can recover the actual data set. So after we recover, this is how the difference looks like. Okay, so let's say this is here we are decompressing it. So here we are saying that this was after reduction, and then this is what we have recovered, and now we can plot the digits. Okay, now we can plot the digits. Can we do the inverse transform on our data set above? Should we try this? Okay, so let's go up. Should we try it? All right, so do you see that? We are importing this, splitting it, training it, and transforming it. All right, and of course, when you are doing the transform, instead of doing the train test, you don't need to do a splitting here. You can do the splitting in your algorithm. You don't. Okay. All right. So we are done here. Then, okay. So this is our new data set. If we try to plot this, okay, we can't really plot it. So what we have to do here is, before plotting, we have to recover this, right? You have to say recovered equals, and we are saying PCA dot inverse transform, and this is our, I'm just trying to see if it can do the reverse transformation. Okay, and we'll try to plot the required one. Okay, so probably it requires Okay, let's try this. I see. Oh, this time the because of shuffling, you can see the difference. Yes, this is the recovered shape, and this was the original shape. This is the recovered image. This is the recovered image. This was the original image. All right. So the same thing we have tried to do here, that when we are at the 95% of the variance, this is the original data set, and this is the recovered one, right? So there's not much of the loss. Can you visualize the loss? Can you see the loss anywhere? Okay. The only thing is the background is converted from white to black. And you can also see that 2 has, I think, become a little once. Okay. So there could be a very tiny bit of error here and there. This is called reconstruction error. Okay. So it has let go of those features which are not required, like the dots surrounding each of the images are not required, so it has let go of those. The problem with PCA, the batch PCA, it requires the entire training set in the memory to run SVD. Okay, so the default version of PCA requires entire thing in the memory, so we can use iPCA. It splits the training set into mini batches. It feeds one mini batch at a time to iPCA algorithm. It's useful for large data set and online learning. Hello? Yeah. Hello? Can we start? Are you able to hear me clearly? Oh, it suddenly stopped working for no reason. All right, great. So let's get started. And all right, so the only downside of PCA is that if you have your data set really huge, then you'll have to load the entire data set into the memory. But the good part is that there are these other versions of PCA which are non-batch, which can basically load that you can do work in parts. So using incremental PCA, you can split the training set into mini batches, feed one mini batch at a time to iPCA algorithm, and it's useful for really huge data sets and online learning. Incremental PCA using scikit-learn's incremental PCA class, and an associated partial fit function instead of using fit and fit transform. Okay, so we can use the incremental PCA in this manner. Okay, so instead of using normal fit, we'll use the partial fit, and that's about it. Okay, another way is to use NumPy memory map class, which is essentially mapping the memory such that in case the certain data doesn't go into the memory, it'll put it into the disk. Okay, so basically it uses the disk instead of the memory. If you have, let's say, a SSD and you want to utilize the disk and your data is not fitting into the memory, in that case, you could use the NumPy's memory map class. So all you need to do is create the data set like this. So here we've created this x_mm. This is a memory map. We are saying np.memorymap and giving the file name. And then we are specifying the data type, and we are saying mode equals write. And the shape is same as the original one. And afterwards, what we are doing is we are assigning the values from original into this. Okay. Afterwards, we can use this x_mm x underscore mm into our work. Okay, so here we're deleting it so that we can recreate it here. And yeah, so we can also use the basically the same method here and use it x underscore mm with incremental PCA. Okay, that way the entire data set will not be loaded into the memory. Instead, it'll be loaded from the disk whenever required. So here is this we have already covered. So here it's going in the increment, and it's basically going iteratively. You can see that the incremental PCA would look slower because it's taking only partial data. It's basically taking only few hundred, there are 100 batches, so it's doing in the 100 batches. Okay, so okay, let me refresh it. I'll have to refresh it. Okay, so okay, I'm going to run all the cells all above. All right. Looks like this part is taking time. All right, now it's plotting this one. All right, so now let's check this part. So it's taking, this one you see that since it goes in the batches, it takes some time. But the good part is that it would not use too much memory. Okay, now here what you have is, let's say we are creating this particular memory map, and then we're loading it. Okay, so that's what we wanted to demonstrate, that you can actually load the data, or say keep the data in the files in case it's not fitting in the memory. Okay, the next part is the randomized PCA. Here we are saying that the SVD solver is randomized. Okay, so it's basically what it does is, instead of finding the best principal component, it tries to just find the approximately best. Okay, it's kind of stochastic. Instead of trying all permutations, it just tries to kind of does it stochastically, and that is generally better. The complexity of this one is lesser. If it's not a function of number of instances, it's a function of number of dimensions. Okay, it's dramatically faster when the number of dimensions are very lesser as compared to the number of instances. So randomized PCA is great if your number of dimensions are far lesser than the number of dimensions are far lesser than the actual number of instances. Okay, so the next one is there is another variation of PCA. PCA first one was using the batch PCA. Then there was incremental, and then there was stochastic, the randomized PCA. Okay, so it's basically a randomized PCA, which basically quickly does the approximation. The next one is the kernel PCA, and the kernel PCA basically does the similar thing what SVM were doing, like apply some kind of kernel tricks, and even it makes it possible to do the nonlinear projections for dimensionality reduction. This is called the kernel PCA, KPCA algorithm. It's important. The important point about the kernel PCA that it's good for preserving clusters, useful when unrolling dataset that lie close to the twisted manifold. If your dataset is kind of twisted manifold, you can't really use the normal PCA. In that case, you will need to use some variation of PCA in kernel form, which is KPCA. Okay, so in case your data is in either of these forms, right, you will need the kernel PCA. For this, you will need a linear kernel. For this, you'll need right. So if let's say you're using the linear PCA, linear kernel, you will get this kind of result. If you're going to use RBF kernel, you'll get this kind of result. And if you use sigmoid kernel, this is how you will get. So it is kind of unrolling it in certain form. Okay, so you can take a look. Okay, let's move ahead. Right? So what's happening here is that, first of all, we used a function called make Swiss roll, which created this Swiss roll data set. Then we used the kernel PCA. And then we use the RBF kernel, and then we use the sigmoid kernel, and then we try to plot it. Okay, so basically, when your data is kind of in the form of the manifold, then you would require a nonlinear kind of model to convert your data set into something that is you will need a nonlinear model to unfold your data, or you can say reduce the dimensions. Okay. All right. Generally, the strategy that we follow is that we basically do the iterations and compare the results across the various PCA algorithms, whether it's kernel or non-kernel one. In both the ways, we do the kind of comparison instead of relying on our hunch. Okay, so kernel PCA is an unsupervised learning algorithm. So there is no obvious performance measure to help select the best kernel and hyperparameters. So what we do is we create a pipeline with kernel PCA and a classification model, and then we do the grid search using the grid search CV to find the best kernel and the gamma for KPCA. Now, what we do is one way to do things is just create a pipeline in which we try all possible kernels, right, and see which one is giving good results, right? Let's say we are working on MNIST and we want to figure out which of the kernels are best at giving the results. So we will try all possible kernels and see which one is giving good results, and then we keep that one. That is the first model, and we will consider that this as one of the hyperparameters, right? The kernel as one of the hyperparameters. We could use RBF, we could use sigmoid, or we could use linear. We will just think of it as if the kernel is just one hyperparameters. Okay. So I mean, this is the most common way, and you should generally follow that instead of any other means. Though it's important to maybe understand it, but not really required for most of the work. That what goes inside the kernel PCA is not really required. Now, the other approach is to do the reconstruction. Okay, like in case you are not using it as part of your machine learning pipeline, in that case, it would be better to just do the reconstruction and compare which one is yielding the low construction error. Okay, the way what we did in case of MNIST, just now, that we applied PCA, and then observe that what exactly has changed, right? First we applied PCA earlier, right? First we applied PCA and we got the new data set. Then we did the inverse and we got the actual data set back. Then we compared the actual one with the reconstructed one, and then we can take a look at what all has changed, right? So this is that approach, right? So there are two kinds of approaches to figure out which kernel is the best. First one is see which one is giving good results. Second one is the one that has the low reconstruction error. Okay, so I mean, reconstruction is generally hard. Okay, so what we do is we take the original space, then we reduce this space, and we do kind of reconstruction and then compare these two, or we compare these two. So basically, from any of these, we try to map it to the original one. Okay, so it is generally a tactical game whereby it's not really possible always to do a one-on-one mapping, and therefore reconstruction error is something you can't really minimize or compare that easily. So the general thumb rule is that if it's part of your pipeline, just try the various kernels and observe which one is giving you good results and pick that one. Okay, so reconstruction error, computation of reconstruction error is not a very great way or very straightforward way. So we generally follow the two-step process. One, okay, so we follow the two steps in kernel PCA, the reconstruction. One is mapping to a higher infinite dimensional feature space, then projecting the transformed training set into 2D using linear PCA. And inverse of the linear PCA step would lie in the feature space, not in the original space. And since infinite dimensions, we cannot compute the reconstruction point. Therefore, we cannot compute the true reconstruction error. Okay, so all right. So here, this was our original space. Then we did kernel PCA. We got a 2D space, and right. Then we applied a kernel and then did the PCA. Okay. Then we basically here. Okay, and so on. All right. So essentially, what we are trying to do is that we want to recreate the original image, right? And see what exactly had given the maximum error. correct? Now, in case of reconstruction of kernel PCA, first of all, we map the kernel PCA. Remember the kernel PCA, it basically generates a lot of dimensions and so on. It basically does all kinds of translation of every data point, and then project the transformed training set into 2D using the linear PCA. So we can use the kernel PCA followed by a linear PCA, and then we do the inverse of linear PCA step, right? And so on. So basically we can try to recreate the pre-image from the original as well as from the kernel one, and then compare the two. Okay, so how should I? All right, let me see if I can give you a better example. All right, I think I'll skip this part. Probably I need a better example here. It's not, none of this is conveying the point. So the sole part is that what we do is, after applying the kernel PCA, we get a certain image, and then we try to do the reconstruction. This diagram is not that accurate and obvious. So what we do is we try to recreate an intermediary image, and then we compare that intermediary image with the original space. And that way we can come up with the reconstruction error. All right, so I think this part we will probably do it again with a better example. Okay, let's just continue with I'll just make a note of it. Okay, so the reconstruction error in case of kernel PCA, we require a better, more friendly example and diagram. All right, now moving ahead, so we will cover this part again. Okay, now moving ahead, now here the Arun, Deepak, Janarayan, Robert, Robin, and Satyajit. Shall we move ahead? Okay. All right. All right, great. Now, this sounds like too much word, but actually it's really easy. The another thing that we have been discussing about is the manifold learning. So far, we learned about one technique called PCA. PCA had multiple ways. One is SVD, other is incremental PCA. Then we had kernel PCA and a stochastic one. And then we showed that how we could do it from the disk instead of loading entire thing into memory and so on. So those were the parts of PCA. Now, the second thing that we discussed was that if our data set is really complex and the PCA is not able to achieve it, in that case, we could use something called manifold learning. Now, manifold learning is basically also called as local linear embedding. That's one of the algorithms that does the manifold learning. Okay, so it's basically nonlinear dimensionality reduction step. Manifold learning, it does not rely on projections. It works by measuring how each training instance linearly relates to the nearby one. Okay, and then looking for low dimensional representation where these local relationships are preserved. Okay, it's good at unrolling twisted manifolds, especially when there is not much of noise. Okay, so what does it mean? It means that whatever data set we have, it first tries to figure out the local relationship with each of the data set. Okay, let's say there is one data set which is close by to another, and like let's say there are 10 such data points to which it's close by. When the manifold, when it unfolds, the nearby data set will maintain the same relationship. Okay, and it's basically a very interesting techniques. So it's like exactly like what we do in case of a bad sheet, right? When we are straightening up the bad sheets, right? every you know particle of the bad sheet is actually associated with the nearby one. And here we're talking about every um, every part of the bed sheet is kind of associated with the nearby one, and it's kind of holding hands with the neighbors. And when we unroll it, those relationship with the neighbors remain as such, meaning we move the neighbors as well as the individual, such that the relationship with the neighbors is intact. Okay, that's what is the unrolling means. That's what it unfolding means. Okay, when we do unfolding of things or unrolling of things 100 times in a day, right? But the most important part is the material that is being unfolded, it remains intact. We don't tear it, right? We don't tear it, we don't break it. The relationship of each of the part is maintained with its neighbors. Okay, so what we can do is we can start with making a Swiss roll. They're using the make Swiss roll example. And then we create we instantiate the locally linear embedding, a number of neighbors with which it needs to keep relationship. Let's say that is one of the parameters. Okay, and okay, and once we are done with it, once we are done with the transformation, we will get a new data set here, and then we can plot it. Okay, so whatever the Swiss roll we had created, when we plot it after unfolding, this is how it looks like. Okay, so Swiss roll is completely unrolled. The distances between the instances are locally preserved. Okay, but they are not preserved on the large scale, meaning relationship between the far apart data is not maintained. Okay, and the right hand side part is stressed, but the relationship, you see, these relationships are maintained, but the relationship between this and this is not maintained, right? So so what's happening here is, I'll just show you visually and then we'll talk about the algorithm. Okay, so let's say this was our data set. Okay, so this data point, or let me just draw the data points. Okay, so imagine that there was one data set like this, and like this. Okay, this is another data set, this is another data point, another one, another one. Okay, like that. Now, this data set is making some kind of a shape here. So this shape will be destroyed when we unfold it. Okay, when we unfold this data set, this shape will be destroyed. Okay, so the way it'll do is it'll first figure out that who are the neighbors for each one. Like for him, this guy is not the neighbor. This person is the neighbor next one. For him, this is the neighbor. For him, this is the neighbor. For him, this is the neighbor, right? So it's kind of, we have noted down who is whose neighbor. Okay, and then when we are moving this, we basically take this and come in a way that present this in a new set such that these relationships are intact. These relationships are intact, right? Though it would not care about relationship between this and this. It let go of this one because these two are far apart, right? Okay. Now this sounded simple when we talked about it using the diagram or in people terms. In reality, it's actually a bit complex process. So what it does is, in step one, for each of the instance, the algorithm identifies the closest neighbor. So the algorithm identifies the closest neighbors. It reconstructs the instances as a linear function of these closest neighbors. Okay, so what it does is it finds that weight vector such that the distance between the closest neighbor and the instance is as much as possible. So the first learning step is find those weights, find those relationships between the data set such that they are closest to each other. Okay, so we find those weight vector such that the distance between the instance and the neighbors is minimum. Okay, so we minimize this over all the instances. So we want to find out this relationship. So what are we trying to do? We are trying to find out the distance between this. We are saying that the distance between this and this, distance between this and this, this and this. So we are computing this relationship. We are computing this relationship. Okay, meaning we are trying to express the neighbor by multiplying certain weights to it as this value and see how we can translate that. Okay, so what we are doing is here, so we find the w vector such that the closest neighbors, so the closest neighbors are nearest. So here we are iterating through, this is me and these are my neighbors. Okay, these are my am neighbors. So this is me, this is my am neighbors. And what we are trying to do is, actually this will go from here, j is not equal to I actually, okay, because I'm not trying to find my own distance. Now, okay, now what we are trying to do is we are trying to minimize this difference. Okay, find such weights such that when we multiply with the weights with the neighbor, the value comes out to be almost 0. Okay, how can find those weights such that your neighbors can be expressed as you. So we try to minimize this. We try to minimize this such that. So what do we try to minimize? We try to minimize this square. Okay, and at the same time, what we are saying is, if here we are saying that in case ij, in case a particular value is not, particular neighbor is really far away, okay, in that case mark this w at 0. Also here what we're trying to do is we are saying that these weights should be, total sum should be 1. All right, again what we are trying to do here is we are trying to find those weights with which if you multiply the neighbors and sum them up, okay, they will be like you. Okay, they'll be like you. That's what we are trying to do, and we are doing it for all the instances. Okay, once we are done with that, we try to relocate them. We try to change their position by maintaining the same distance or same relationship. Once we have figured out those weights, these weights, not this weight, these weights, okay, once we have figured out those weights, then what we can do is we can translate xi into zi such that this remains smallest. Okay, so in simple terms, what we are trying to do is, first of all, we figured out who are my neighbors, real neighbors, not far away neighbors, who are my real neighbors, nearby ones, and then we are preserving the distance between me and my neighbors, and moving to a new distance. So it's like taking one civilization from one place to another. It's only the real estate change. People remain the same. Okay, people remain the same. First, they were neighbors in a particular village. Then they are now neighbors in various floor or of a big apartment. The relationship remains same, though the place, the whole environment, their various locations have changed. Okay, so basically that's what is happening here. Basically, keeping the same weight as calculated previously, the new instance should have the minimum distances with the previous closest neighbors, same weights and relationships. Okay, so basically moving people from one geographical location to another geographical location while preserving the relationship as same, right? That would not make difference to people if they have the same neighbors, same same family, and everything is same. If they move to a different location, it would remain the same, right? That's what is happening here. We first of all noted down everyone's relationships, everybody's neighbors who are good friends and all, and then in case there are people who do not matter to you or who are distant, it doesn't matter anyway. So those relationships we are not caring much about. So that's what is, it's like house moving thing. We first figure out that these dots are related to these instances are related to each other, note down their relationship, and then we move them to a new territory, keeping the same relationships. So that's what is happening here. So we are mapping that xi to zi such that the distance between original relationships and new relationships should be minimized. That's what is happening. Okay. So I hope theoretically you got the idea of LLE, right? So in a LLE, all we do is we find out the nearest relationships by the way of normal machine learning steps. Okay, and then we unroll them, unroll as in change their coordinates such that the new coordinates should also have the same relationships as earlier, right? This is what we do. So basically, keeping the same weight as calculated in previous step, the new instance should have the minimum distances with the previous closest neighbors and same weights and relationships. Okay. So here the complexity of this algorithm is a little higher side. Okay. So first step is to find the neighbors, then finding the relationships, and then constructing the low dimensional representation. Okay, we let go of those relationships which don't matter, and that's basically the data loss, or you can say the reconstruction loss. Okay, so we're constructing the low dimensional representation, and so you can see that this is the overall, this plus this plus this. That's the overall complexity. Okay, so whichever is the maximum, that's the one which you'll pick. Probably this will be the maximum out of all. So m into n multiplied by log m into log k, and this k are the nearest neighbors that we're looking for, and probably therefore I believe that this is going to be the most costliest affair here. No, actually this also. Since m is really huge, therefore this number is also going to be huge. Okay? But the d is smaller, but n is higher. Okay? So this is the complexity that it requires to do the LLE. First step is finding the k nearest neighbors. Second step is weight optimization. Third step is constructing low dimensional representation, okay, and so on. So these are the 3 steps that are done, okay. Probably that's what was done in times of the 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 civilization movements in past, whereby basically, if let's say the government needs to move a certain civilization to a new territory, first of all, they have to make a note of who is whose neighbors, who is whose, how many neighbors each one has, and who has what kind of relationship, and then like this is the family, this is the pet, this is the neighbor, and so on, and then figure out those relationships such that the relationships are the weights are minimum, okay. Only the most important relationships are kept, and afterwards when we move the civilization or move the instances, we want to keep the same relationships, and we let go of the relationships which did not matter much, okay. So this is basically LLE. LLE helps you unfold the complex data sets, specifically in the form of manifolds, right? So the other multidimensionality scaling techniques are MDS, which also does a similar thing what we have done before. And there is ISO map. It creates a map connecting each instance to its nearest neighbors, okay, and so on. And then there is something called T-distributed stochastic neighbor embedding. It reduces dimensionality, keeping similar instances close and dissimilar apart. It's mostly used for visualizing the clusters in high dimensional space. Then there is something called LDA. It's a classification algorithm. During training, it learns most discriminative access between the classes. Access can be used to define the hyperplane to project the data. Okay, and projection will keep the classes as far apart as possible. It's basically same as what we did in SVM, right? So it's a good technique to reduce dimensionality before running the classification algorithm such as SVM. So LDA is essentially another classification algorithm. During training, it runs the most discriminative access between the classes, right? And the access can be used to define the hyperplane to project the data. All right. Now, right. So this is another technique for doing the dimensionality reduction, and you could take a look at them and see which one makes sense to you. Out of this, we generally use the PCA for dimensionality reduction if the data set doesn't have manifolds. Okay, the LLE is good, but it takes a lot of energy, so people use KPCA in those cases. All right. So this is another one. Okay, so we basically use the PCA or kernel PCA. Okay, only in certain cases when we see that the data set is really complex and it is not coming down, in that case we could give it a shot to LLE. Okay, all right, this is how it looks like after unrolling. And then there are other methods, so you can take a look at the other methods here. They're all part of manifold learning: MDS, ISOMAP, and TSNE. All right, so this was the dimensionality reduction part. We will talk about the reconstruction error of the kernel PCA part, probably at later point of time, and if time permits. We require a better diagram over there. All right, so One more thing I would like to discuss today is the naive Bayes. It's actually a pretty simple thing, so I can quickly cover it. Okay. So naive Bayes is basically most primitive algorithm that you can think of. Okay. Okay, it's actually really primitive and simple. We do it every day as our general behavior. We use the naive Bayes all the time, right? So classification techniques is based on Bayes theorem with naive assumption of independence amongst the predictors. It's easy to build. It's particularly useful for very large data sets, and it is known to perform even very highly sophisticated classification methods. Specifically, earlier there were sophisticated methods of spam detection, and in that it did perform really well. Okay, but it's actually really primitive method. I'll explain to you. Don't fall for this formula. Okay, so here the idea is that we basically compute the probability of something when some other thing has happened. That's called the posterior probability. Here, the way we are representing things is in this form. We are saying P C by X, meaning the probability of the posterior probability of a class C given the predictor X. Okay, we are given the predictor X that this is the given that the X has already happened. What is the probability that C would C would happen, right? The probability of C, the prior probability of a class, and here what we are saying is, okay, let me just read it out and then we'll talk. So then here here Px by C means it is the likelihood, which is the probability of the predictor given class. Px is the prior probability of the predictor. Okay, so it means here, I think I'll better take an example that will make more sense. Okay, now imagine that we know that, okay, and okay, I think better idea would be just take an example instead of, yeah, I think better example is this. Okay, imagine that we want to predict whether given the weather, can we predict whether will play or not? Okay, we are training using a data set of weather and corresponding target variable called play. Right, now we need to classify whether players will play or not based on a weather condition. Let's say given sunny, will people play? Given rainy day, will people play? Given sunny as well as overcast, will people play? That's what we want to predict. And we are given this historical data that when the weather was sunny, people did play no, overcast, yes, rainy, yes, sunny, yes, and so on. So what we do as part of this is we basically convert our data set into frequency tables. Okay, we basically convert our data set into frequency tables, and here this is a frequency table. It says that if the weather is overcast, how many times did we play? 4 times. If the weather is rainy, how many times did we play? 2 times. And how many times we did not play? 3 times. Yeah. And if the weather is sunny, these many times we played and these many times we did not play. Okay. Now we got the overall grand totals as well. That overall, these many times we had the the game did not happen, and these many times game did happen. Okay. Now the likelihood of overcast is how much? Okay. The overcast has happened four times overall. Rainy has happened 5 times, and sunny has happened 5 times, and so on. So the probability of overcast is 4 out of 14. Probability of rainy is 5 out of 14, and probability of sunny is 5 out of 14. So essentially, we prepare this frequency table. This is our feature and this is our target. So what we do is for each of the feature, we count the targets and we prepare this frequency table. Now we know that what is the probability of happening overcast, rainy, sunny. Similarly, what is the probability of not playing and playing, right? These are the 5 numbers we have calculated. Right? Now, this is the point where we apply the Naive algorithm. This is the Naive theorem you remember in probability, whereby we say that probability of playing, which is yes, if the day is sunny, is equal to probability of sunny when we played into the probability of playing divided by probability of sunny, right? So this is the Naive theorem, which says that this is how we need to calculate. So if you want to find out whether people will play, if it's sunny, then what we have to do is, first of all, find out how many times it was sunny when we played, multiplied by how many times we played, divided by how many times it was sunny. Okay. So this essentially is the Naive theorem. Now, here we have like the probability of sunny when we said yes. The probability of sunny when we played yes is this much, right? 3 by 9. 3 by 9. Do you see it anywhere? Probability of sunny when it was yes. Okay. So this is sunny, and out of total, it is 9. So 3 by 9. 3 by 9. So probability of sunny and probability of sunny and playing is 3 by 9, right? So when we played, what was the probability of sunny? This is 3 divided by total times how many we have played. Then probability of sunny alone overall is how much? 5 out of 14, right? There were total 14 times it has happened. Okay, so out of 14 times, the sunny days were 5.36, and the probability of yes, saying yes or no, is this much. Okay, so we got 0.64, and this way we can now compute probability of sunny given yes multiplied by probability of yes divided by 0.36, right? And then we get the idea that if it is sunny, the chance of playing is 0.6. Okay, so if we are told that today is sunny day, there is high probability that we will play. So basically we are trying to correlate the past with the current. Okay, it's like that in a class we know that which student is how naughty, right? If we know that which student is how naughty, meaning how many times they have been found naughty in the past, if we know that and something has happened in the class, the first we'll think of that it is done by this person, okay? Or given a person the chance of an accident happening, we can calculate, okay? So given a person, we can compute the chance of happening something based on the historical evidences, right? Similarly here, what we are doing is probability of no if it was sunny, the same method that we applied earlier, we are applying again, and this way we can calculate the probability of saying no when it was sunny, okay? All right, now there could be many things, right? There could be many parameters. One is outlook, temperature, humidity, windy, and based on these 4 columns, can we predict the 5th column, which is the golf will be played or not? Okay, given this data, the problem that could be asked to you is that if a day is rainy, mild, normal, and the outlook is rainy, temperature is mild, humidity is normal, windy is yes, in that case, do you think that the golf will be played or not? Okay. In this case, what we do is we consider each of these parameters independently, each of the columns independently, and prepare these tables. Prepare the frequency tables. And once we are done with preparing the frequency tables, then we can apply the same formula that we used earlier. So if the outlook is rainy, temperature is mild, humidity is normal, and windy is true, will we play or not? What we'll do is we will compute the likelihood of yes. So first of all, we'll say that the given, right? So given that the outlook is rainy, what is the probability of yes, multiplied by given the temperature is mild, what is the probability of yes, given that the humidity is normal, what is the probability of yes, and then we multiply all of them together, and then we multiply it by yes. Okay. All right. So the probability of yes when it was rainy, probability of yes when it was rainy, probability of yes when it was rainy is 2 by 9, multiplied by probability of yes, probability of I'm saying the other, probability of mild temperature when it was yes, it is 4 by 9, 4 by 9, probability of humidity being normal when game was played, humidity being normal, game was played, which is 6 by 9, then multiplied by probability of windy when the game was played, it is 3 by 9, and then probability of yes, 9 by 14. What is the probability of yes? 9 by 14, right? So that's the overall probability. You can take a look at this one. How many times the game was played overall? That's what we are multiplying there. So given these conditions, the likelihood of yes is 0.014. And what is the likelihood of no? Likelihood of no is 0.0. All right, let this hide. 0.0103. So still, the probability of likelihood of yes is greater than no, and hence the game will be played. Okay. So that's the probability of the two instances. So the answer is that the game, we will play the game given these circumstances. I mean, the chances are that we will play the game will be played given these circumstances. Okay. So everywhere we are dividing by the counts. Here you can see that we are dividing by the counts. And what if the counts are 0? In many cases, what happens is that if the count of something is 0, it becomes like divide by 0. Therefore, what we do is we just add by 1. Okay, we just add the values by 1. In all, add the counts for each one as 1. And that's pretty much. So basically, this is the naive Bayes. So scikit-learn provides a Gaussian NB class, which also has the fit and predict kind of model. During fit, it prepares the frequency table. During predict, it takes the instance and does the prediction. Okay. Okay, so it sounds really, really simplistic model because it is not considering the relationship between the various parameters, various columns or various fields or various attributes. Just checking the individual probabilities and overall probabilities to find out whether something will happen given these circumstances. And therefore, this is pretty naive approach, though it works in word frequencies and other techniques, but that has been replaced with now the word embeddings and neural networks. So also notice that it does not require too much of data, only like basic amount of data is sufficient. If continuous features do not have normal distribution, we should use transformation or different methods to convert. Okay. Basically, this is good only in the cases where the data is in normal distribution. If the test data has 0 frequency issue, right? In case there is a 0 frequency something is having, it'll be divisible by 0. Therefore, apply smoothing techniques called Laplace smoothing, meaning add 1 to all or add a tiny value in everything. Okay. Then next is remove correlated features. If there are highly correlated features, they'll be voted twice in the model, and it can lead to overinflating importance. Naive Bayes classifiers has limited options for parameter tuning. It can't be ensembled because there is no variance to reduce. This is another important point to keep in mind, that since there is no difference between one algorithm to another, therefore it cannot be ensembled. Okay, so there are other variants of the naive Bayes. One is Gaussian, other is multinomial, other is Bernoulli's. You can take a look at those here. Okay, I can just share the presentation with all of you. The application of naive Bayes are real-time prediction. Naive Bayes is an eager learning classifier. It is sure, very fast. Okay, it could be used for making predictions in real time. If you are hard pressed for doing things in real time, then you could choose naive Bayes. It's simple, but it gets something done. Okay. So the applications of naive Bayes are text classification, such as taking the text and computing the frequencies and then bucketing them. Second is the spam filtering. The other is sentiment analysis. This was the most primitive technique that was used earlier. And then in recommendation systems, we use these naive Bayes kind of classifier or some kind of similar techniques in cases where we don't have too much of data, or where we don't have too much of dependence in the columns. In those cases, the naive Bayes works well. All right, so you can take a look at the naive Bayes somewhere here. and these are the parts. All right. So we will have a small class on next Saturday. We will discuss the remaining part that we have not discussed yet. Also, the with respect to the projects one is the ride sharing one that you have to complete. We will continue from here in the next session. Bye bye. Have a good day.